The Picometer precision problem. ESA just signed a €26 million contract on May 5, 2026, to build telescopes that must maintain optical alignment to within a few picometers while separated by millions of kilometers of vacuum. The Laser Interferometer Space Antenna, or LISA, is now transitioning into its hardware manufacturing phase with a specific technical hurdle: the need to detect a distance change smaller than the width of an atom across a triangle 2.5 million kilometers wide. This level of precision is the only way to detect the low-frequency gravitational waves generated by supermassive black holes, escaping the terrestrial noise floor. Terrestrial detectors like LIGO are effectively deaf to the most significant gravitational events in the universe because Earth itself is too loud. Seismic noise, atmospheric density fluctuations, and local gravity gradients create a noise floor that drowns out everything below 1 Hz. By moving the detector into a heliocentric orbit trailing Earth by 20 degrees, LISA eliminates these planetary vibrations entirely. This allows the mission to target the millihertz band, where the mergers of supermassive black holes, objects millions of times the mass of our Sun, resonate at frequencies Earth-based interferometers cannot reach. This shift in location is a physical necessity to bypass the seismic limit of a cooling planet. Phase tracking the Picowatt. Measuring distance over millions of kilometers is not a simple bounce-back operation, because a laser beam fired from one LISA spacecraft will spread to a diameter of 20 kilometers by the time it reaches its target. A standard reflection is physically impossible due to signal loss. Instead, the mission uses transponder phase locking. Each satellite acts as an active relay, detecting a few hundred picowatts of incoming light and using it to synchronize its own local laser before firing it back. Think of it like 2 clocks that must remain synchronized to within a trillionth of a second, while separated by the distance from the Earth to the Moon 6 times over. The engineering risk mitigation. The new telescope contract marks a strategic pivot in mission management. Originally, NASA was slated to provide the telescopes and laser systems, but recurring budget instability in Washington throughout early 2026 forced ESA to develop independent European hardware to protect the mid-2030s launch window. This engineering hedge includes the development of the charge management device, which uses ultraviolet light to bleed off electrostatic charges from the gold-platinum test masses. Without this non-contact discharge system, the cubes would be pulled by the spacecraft's own electrical field, ruining the gravitational purity required for the measurement. This is a case where geopolitical budget shifts dictate the final hardware configuration of the observatory. The gravitational spectrum shift. The transition from ground-based interferometry to space-based arrays is a shift from hearing single violent events to observing the persistent gravitational background of the galaxy. By solving the phase-locking problem across millions of kilometers and the electrostatic isolation of the test masses, LISA transforms from a concept into a permanent observatory for the millihertz spectrum. This changes the dataset from isolated black hole snapshots into a continuous record of galactic growth and white dwarf populations. For the engineer, the takeaway is that Earth's seismic noise is no longer a ceiling for precision measurement, provided we can manage the thermal stability of a triangle larger than the Moon's orbit. The next critical checkpoint is the upcoming 2026 LISA Symposium in College Park, which will finalize the design lock on the laser frequency reference hardware. Subscribe for more.